Picture this. You walk into a dark, completely unfamiliar room. Within seconds, you naturally turn your head, take a few steps, and build a mental map of where the walls, the sofa, and the door are. It's totally effortless for you. But for today's most advanced artificial intelligence, this dynamic physical reality is an absolute cognitive nightmare. Welcome to today's Explainer. We're unpacking a groundbreaking new paper that reveals a massive blind spot in modern AI, and we're going to explore exactly why our smartest machines get completely lost when they have to actually navigate the real world.
Okay, let's dive right into our roadmap for today. 1. The AI spatial problem. 2. Defining theory of space. 3. Testing AI exploration methods. 4. The active-passive gap. 5. Uncovering AI belief inertia. And 6. The future of embodied AI.
Section 1. The AI spatial problem.
To really figure out why AI struggles with space, we first have to look at how we typically test it. Honestly, our standard testing has been giving us a bit of a false sense of security about what these models can actually do. See, there's a fundamental difference between passive AI and active AI. Right now, foundation models, the massive engines behind tools like ChatGPT or Claude, they are incredibly good at passive tasks. If you hand them a perfectly framed static photograph of a living room, they can perfectly list all the objects in it. But embodied intelligence that actually exists and moves in a physical space, doesn't work like that at all. In the real world, you have partial observability, you have to actively decide where to move, when to rotate, and what to look at next to reduce your uncertainty. Real intelligence is about actively gathering your own information, not just passively analyzing a fixed photo.
And that brings us to the core source material for today's Explainer. The paper is titled, Theory of Space: Can Foundation Models Construct Spatial Beliefs Through Active Exploration? This is an absolute powerhouse collaboration. The lead authors are Pingyu Zheng, Zihan Huang, Yu Wang, and Sheiyu Zhang, representing heavy-hitting institutions like Northwestern, Stanford, the University of Washington, and Cornell. They set out to solve a massive problem. How do we shift from just testing passive AI reasoning to actually evaluating how well an AI can actively construct a belief about a space over time?
Section 2. Defining theory of space. To tackle this problem, the researchers had to invent a completely new conceptual framework. They actually drew inspiration from a very famous concept in human psychology. You've probably heard of theory of mind, right? That's our human ability to understand and model the hidden mental states, intents, and emotions of other people. While this paper proposes something called the theory of space. Just like theory of mind measures how we model the hidden inner workings of a brain, theory of space assesses how an AI models the hidden physical structure of a room that it can't fully see all at once. It's basically about building an internal cognitive map.
So the crucial point here is this precise definition. Theory of space is the ability to actively construct, revise, and exploit an internal spatial belief formed through active exploration. The researchers aren't just testing whether an AI can wander around and eventually bump into a chair. They really want to know, is the AI actually building an accurate, working mental model of the room in its head as it moves around? And, more importantly, can it maintain that memory? Section 3. Testing AI exploration methods.
That sounds great in theory, but how do you scientifically test something like that? Well, the researchers built a benchmark testing environment that forces the AI through 3 mandatory operations. First, construct. The AI has to move around and stitch together partial observations into a cohesive global belief. Second, revise. The AI must dynamically update its mental map when the environment suddenly changes. And third, exploit. The AI has to utilize that internal belief to pass downstream spatial tests. Basically, it has to prove that its mental map is actually useful for doing things. Imagine what this testing environment actually looks like from the AI's perspective. It only gets a localized 90-degree field of view at any given time. It can't see behind itself, and it certainly can't see through walls. But what's truly novel here is a feature they call spatial belief probing. At every single step of the journey, the researchers force the AI to output a JSON code file detailing its current cognitive map. It's a remarkably cool approach. They literally crack open the AI's digital brain mid-exploration to see exactly what it thinks the room looks like at that exact second. And once the AI thinks it is mapped to the room, it gets tested on 2 very different levels to fulfill that exploit phase. First is route-level belief. This tests egocentric reasoning, meaning from the AI's current perspective, if it turns right, what will it see? The second is survey-level belief. This requires an allocentric, bird's-eye view understanding of the entire space. It forces the AI to map global 2D coordinates for all the objects in the room, just from memory.
Section 4. The active-passive gap.
So how did the top-tier, multi-billion parameter models actually perform when dropped into this environment? Get ready for a massive plot twist. Take a look at the performance drop for GPT 5.2. When you spoon-feed GPT 5.2 a pre-collected history of observations, meaning it just sits back and acts passively, it scores an accuracy of 0.57 on spatial tasks. But the moment you force it to autonomously gather its own information, to decide for itself where to look and move, that accuracy plummets to 0.46. This definitively proves that active exploration is a massive, unresolved bottleneck for modern AI. When you map out the exploration cost, the inefficiency is just glaring. The researchers compared these cutting-edge foundation models against simple scripted proxy programs that were coded just to efficiently sweep a room. The advanced AIs, they wander around in a highly unsystematic, redundant way. Honestly, it's like watching a completely lost tourist who absolutely refuses to ask for directions. They take far more steps, expend way more energy than the simple proxy scripts, but they completely fail to match the proxy's efficiency, and they produce worse final results. They literally just do not know how to systematically gather information. Which leads us to the second, perhaps even more counterintuitive twist. The paper found a massive modality gap. Now, you would naturally assume that visual models, AI designed specifically to process images, would absolutely dominate in a 3D physical room. But they don't. Pure text models, processing symbolic word coordinates like the chair is front left and near, significantly outperformed the cutting-edge vision models. The vision models struggled terribly to accurately estimate basic spatial details, like which direction an object was even facing.
Section 5. Uncovering AI belief inertia.
Now, what's really interesting here is the most fascinating cognitive failure discovered in the entire paper. It happens when the researchers start playing tricks on the AI using what they call the false belief paradigm, leading to a phenomenon known as belief inertia. Here's how it works. The AI explores a room and maps it. Then, behind its back, the researchers move a chair. The AI re-explores the room and literally looks directly at the chair in its brand new location. But instead of updating its map, the AI suffers from belief inertia. It struggles to overwrite its original memory. It completely persists in believing the chair's in the old spot, totally ignoring the new sensory evidence right in front of its digital eyes. And when you look at the numbers, the severity of this issue is wild. In a text-based world, GPT 5.2 exhibits belief inertia about 12.5% of the time. But in the vision-based world, that error rate skyrockets to nearly 35%. That means more than a third of the time, the vision model entirely lacks the cognitive plasticity to revise its internal map when a physical object moves. It is essentially hallucinating a past reality over the present one. So what's the bottom line here? Well, vision acts as an initial bottleneck, but the deeper, more structural issue is that the AI's internal global map is highly unstable. The researchers call this belief drift. Even if the AI perfectly perceives the room on turn 1, by turn 5, that memory degrades. New, sometimes incorrect updates actually corrupt the earlier correct memories. The AI simply cannot hold a stable, working physical model of reality in its memory over a long period of time. Section 6. The future of embodied AI. So what does this highly technical, dense academic paper actually mean for us in the real world? It turns out, pretty much everything. If we ever want autonomous robots interacting with us safely, this research is the key. Right now, companies are racing to build robots to fold our laundry, clean our messy, dynamic homes, or navigate busy city streets. But this paper proves that before we do any of that, we have to solve the theory of space. We have to develop AI policies that are actually aware of their own uncertainty. We absolutely need reliable spatial memory for long-term tasks. And eventually, we need to figure out how multiple AI agents can coordinate and share these spatial beliefs without their mental maps just collapsing into a mess of errors. Which leaves us with this final, profound thought. Foundation models have completely mastered the art of talking like humans, and they can easily ace tests on static images. But if a cutting-edge AI cannot successfully update its internal mental map just because someone moved a chair across the room, how can we possibly trust it to navigate the beautifully messy, unpredictable, and ever-changing physical reality that we live in?
It is a massive hurdle for the future of embodied intelligence, and I highly recommend checking out the full paper to see how these brilliant researchers are paving the way to finally solve it. Thanks for learning with us today.